Okay, welcome to class. Welcome to your Wednesday. Okay, let's start by doing a reading quiz, because we didn't do it on Monday, because it was the day after the exam. So a lot of these questions are from the reading, but we covered them on Monday already. When a crack splits through grains, this is called transgranular cleavage, and it is a hallmark of ductile fracture or brittle fracture. Okay, answers in transgranular. Oh, that's supposed to say transgranular. That's a typo. And if it helps at all, when it is transgranular and it splits through the grains, that makes it a more flat surface. So is that ductile or brittle? Okay, so answers in. Okay, we're gonna wrap up this poll. So if it's a flatter surface, that is definitely brittle. Okay, let's do the next one, which is fracture is spontaneous, meaning that the crack growth is unstable, right? It's going to happen on its own without having to mess with it. When what two energy terms are equal to one another? Free energy and surface energy and chemical energy, strain energy and free energy, or strain energy and surface energy. Okay, wrapping up the poll. Is it A, B, C, or D? If you don't know, phone a friend. We're going to end right now. Okay, definitely the last one. Okay, one last one. What is the main difference between ductile and brittle fracture? A, ductile fracture absorbs a lot of energy and has a significant amount of plastic deformation. B, brittle fracture absorbs a lot of energy and has a significant amount of plastic deformation. Or C, ductile fracture is not associated with creep, but brittle fracture is. Okay. People think, everyone thinks it. Oh, everyone got the right answer. That's amazing. Has this happened before? Well done. Well done. Okay. So last time we left off, we did our first calculation of what we call Griffith fracture toughness, right? Griffith fracture toughness, we're going to come back to it over and over. I guarantee there will be a question that uses it on the midterm, the next midterm, there always is. And the key to using the Griffith fracture toughness equation is the following. You've got the left-hand side of your equation, and you've got the right-hand side of your equation. the left-hand side of your equation is a fundamental materials property, right? So you look up some alloy or some material or whatever, it has just a fundamental property. On the right-hand side of your equation are things that can change based on your experimental conditions. For example, the crack size and the loading, as well as the crack geometry. If at any point the right-hand side of this is greater than the left-hand side, it will fail in brittle fraction, right? It'll spontaneously crack, okay? That's as simple as it is. If the right-hand side of your equation is larger than your fracture toughness, it will fail, right? Or in other words, if you know what the fracture toughness value is, like we did in this problem, we told you it's 60.4 megapascal root meters, then you can figure out what will make it fail by making the left-hand side equal the right-hand side, right? In this case, we knew what load we were going to apply, and we asked the question, how big can the flaw be, right? We could have done the opposite. We could have said, all right, there's a flaw in your material that's 5 millimeters big. What's the highest load that this component can sustain, right? And you would solve for sigma in that case, right? So there's lots and lots of ways to ask questions around this because there's multiple variables that we could choose to ask about, okay? We'll do another example of it later today. Today, our learning objectives are, first, identify what is static fatigue and talk about how that relates to failure of ceramics in particular. We'll describe crazing. We'll talk about impact testing and ductile to brittle transitions. We'll use SN curves to observe what's called the fatigue limit. Fatigue, like things get tired, materials get tired when you use them over and over. Similar concept. And then we'll probably only have time to do Paris's law to predict crack growth. But if we do have time, we'll get into creep of materials. Right? So let's start with static fatigue. When ceramics break, as everyone got right on the clicker question, there is no plastic deformation. Again, we gave the example of your dinner plate. You can't flex that at all. Like a piece of chalk is ceramic. You can't flex this at all. It'll just break if I keep trying to bend it, right? Whereas other things like a rubber band, you can deform quite a bit and it doesn't break, right? The stress razors are typically pores or impurities. And because these things can't accommodate any plastic deformation, they tend to have really low fracture toughness values, the lowest of pretty much everything. Some polymers are lower, right? So when we say low, what's a low value? Well, they're typically less than 10 megapascal root meters. That's low for most ceramics. Whereas metals like steels and aluminums can be 20 or 80 or different values. And polymers can be kind of in between, actually can be around ceramics, okay? Something called slow crack growth is possible, right? So here's our Griffith fracture toughness equation. Oops. Right? And I said if at any time the right-hand side of that equation is larger than the left, or once it's equal to it, this thing will fracture. So something that can happen is this. Initially, your crack size is small, right? But as you cycle this thing in use, maybe you're pulling on it and compressing and you're going back and forth. If you do that over and over, what can happen is your crack can grow over time, right? Cracks don't have to stay the same size. They can steadily grow. And as it grows larger, it can reach a critical size. Oh, gosh. Right? It can reach today's going to be one of those days where one note ruins our life. It can reach a critical size, right? Definitely going to be one of those days. Let me stop this and restart it. And hope that fixes things. I think it's having a phantom touch issue on the screen I need to get fixed. Okay, so if that thing grows, it can grow large enough that you will actually fail, right? So we need to determine what will make it grow. One thing that can make it grow is when you're not even cycling your stress, it can still fail. This is called static fatigue, meaning you apply a load to it, and that load causes it to fail, even though that load is static. What's typically happening is at the tip of the crack is growing. If a little bit of water, for example, gets at the tip of the crack, it can dissolve the material at the tip of that crack. Now, normally you don't think of a ceramic as being particularly soluble in water, but when it's a really small radius of curvature, so therefore a high curvature, then your solubility can be much higher. So the very tip of that crack actually can be dissolving, and that makes your crack continue to grow, right? That's one possibility. Because of that, they'll call this stress corrosion cracking sometimes. And if you have a ceramic that's going to be in liquid, they can be particularly susceptible to this. Where basically, again, you're dissolving away your material. So it starts out in some crack length, and as you slowly dissolve it, that crack just gets longer and longer and longer, okay? Eventually, it's going to be long enough that it satisfies the critical flaw size and the single fracture. You can see this, by the way. If you scribe a piece of quartz tubing and you try and break it, it's pretty hard to break. That stuff's pretty strong. But if you just like dip that under water after you scribe it, now you've got water at the tip of that crack, you can pop it at least, you know, half the strength. It's much easier to break. All right, let's talk about polymers. When polymers fracture, typically the yield strength, these things are not as strong as metals or ceramics, but they can deform a lot more, right? You have thermosets and thermoplastics. We'll talk about those in a couple chapters. What's the difference? Yeah, question?
What exactly is yield strength?
Great question. We're going to come back to it. Let's talk about, that's the point where it starts to deform. The yield strength starts to yield. We will come back to that in a few chapters. But yeah, for now, think of it as you're going to apply a load until it starts to bend or something. Yeah, question?
I know we're going to go through that, but the never back point.
Yeah. Yield, once it's permanent or plastic deformation as opposed to elastic. So rubber band, you take a rubber band and stretch it. We say rubber bands are, you call it an elastic band, right? Because it's elastic, you stretch it and it goes back to where it started. If you pull it too far, you now enter the plastic regime where it's permanent. It's non-reversible, okay? There's two different types of plastics. One tends to be more brittle, one tends to be more ductile. We'll come back to this, so you don't need to know this just yet, but like, and you've probably seen this, like an old, like imagine like a 50s era telephone. That's a plastic, but it's not very forgiving one. If you drop that, it could actually break into pieces. It's kind of brittle. Whereas a lot of plastics, like a G.I. Joe guy, if I bend him in half, it's not going to break, it's going to bend, right? Of course, it does depend on two things. It depends on temperature, and it depends on the strain rate. That's the critical thing. Remember the banana? The banana could be very, very ductile, or it could be actually pretty brittle depending on whether you break it fast or if you break it at a high or a low temperature. So temperature and strain rate are critical for determining ductile versus brittle. And then you can also get something called crazing occurring. Crazing is when you get these regions of localized yielding that connect the crack, right? See these little bridges happening in this thing? You see those little bridges forming? That's called crazing. Do you think that that increases or decreases the fracture toughness? It should increase it. How would you guess that? Well, what are our two rules of thumb? To make a material tougher, you have to do one of two things. You either have to, anybody? Maybe tell your neighbor what you think the two things were. To make a material tougher, what can you do? Okay, let me ask David in the Alaska shirt. What is one thing that you could do to make a material tougher?
Like add something else to it, change the composition of it.
Okay, how would it make it tougher? What's the mechanism that's happening?
Changing like the type of impurities or voids that are in it.
Okay, maybe I just want to add on? Yeah.
Maybe make a crack, make it do that.
Yeah. Remember, the two rules of thumb is if you make it harder for the crack to propagate, like a secondary phase like you added, maybe it hits that secondary phase and has to go around it or something. Or, yeah, question, Rosa?
So are you saying that that's a crack, but it's characterized by crazing, and crazing makes the crack harder to crack more?
Yeah, because for that crack to continue delaminating, it has to pull out those bridges, basically. So if you make a crack harder to extend, or if you make it harder for a crack to start, either of those things will increase the toughness of the material. And another way to think about toughness is how much energy gets dissipated as the crack moves forward. In this case, if you've got a bunch of little bridges in there, that's dissipating a lot of energy, right? You have to put energy into that, so it's storing more energy as the crack grows, so you made a tougher material, okay? So crazing is good, and it's why polymers don't have a lower fracture toughness, right? Because they're typically characterized by having crazing occur. Yeah, Spence?
How do you cause crazing? How does that happen?
Let's wait till we get to the polymers chapter. We'll come back to it. So we will return to polymers. Oh, that was a clicker question. We already did that one. All right, get your free clicker question. Did crazing increase or decrease fracture toughness? We just did this, so everyone get your answers in. Yeah.
Do the bridges form parallel to the
the loading direction. Yeah, they don't have to. I'll show you some examples later on. You can have like a laminate structure, like a bunch of plies laid up, and when you try and pull that apart, you'll still see some bridging like that. So they can occur both ways, and it depends. If you're talking about a composite, you can engineer it to be one way or the other, actually. Okay? Okay, so answer's in, 100%. Will it happen again? Oh, sorry. Okay. All right, how do you test fracture toughness, right? Fracture toughness is, again, it's this quantitative like material property that tells you how resistant to fracture something is. So how do you test that? We'll talk about fracture toughness in terms of energy in a few chapters. But one thing you can do is you can look at how much energy gets absorbed before versus after, right? So you take a pendulum. Mechanical engineers, have you guys used one of these before? You haven't used one of these fracture toughness. You start it out and you note the position that this pendulum is at. So it's pretty heavy weight. Your sample is sitting down here at the bottom, and your sample has a little notch in the middle so that it breaks in a specific spot, right? And this hammer basically comes swinging in, right? It comes swinging in right here, and it hits your sample. And when it hits it, it's going to break it. You know, if it's brittle, it'll break it. And then that hammer's going to keep on swinging, but it won't go up as high as it started, right? There's going to be a difference in the height of your starting point and the height of your ending point because some energy got transmitted to your sample, right? And so this is a tool that basically measures the energy as you create these new surfaces and as you strain the material, right? So it's a measure of fracture toughness. So they do this. They'll do these Sharpie notch testing is what they call them, Sharpie pendulum or Sharpie notch tests, right? They'll do them at different temperatures, and you often see this behavior. Some materials will exhibit what's called a ductile to brittle transition. So this mild steel, for example. Now, which side is ductile and which side is brittle? Turn to your neighbor and take a guess which one should be which. Like, here's clearly the transition temperature, somewhere around here. Which side is which? Okay, let me pick on Ari. What do you think? So she thinks that the higher side, so on the right, is ductile. What's your rationale? Yeah, it's just absorbing more energy. If you're absorbing more energy, you must have made it harder for that crack to travel through. You must have made a tougher material. And almost always, in fact, I don't know of an exception, you have ductile materials at high temperatures, and if it becomes brittle, it'll be at low temperatures, not at higher temperatures, right? So when you cool things down, they become more ductile. I don't think vice versa, right? But not all materials have this behavior. Some it's really remarkable. So some type of steels, this is a big deal because imagine that you're in World War II, right? Or Takara, question? Great question. Your ductile transition could be associated with a phase change. I'm talking about with a single phase that increasing it doesn't make it more brittle. But you're right. If you go from a low temperature phase to a high temperature different phase, that could be more brittle. So that's actually a really good observation. If you're in World War II, which we were, right, and you were making boats to go into the Baltic, which we were, they tried to make them as quickly as possible because our Navy got decimated, right, and we basically had to start from scratch. So we made boats as quickly and cheaply as possible to try and get up to speed in the war, and we made what were called Liberty ships. Liberty ships because we made them quick and they were going to spread liberty or at least prevent us from losing the war, right? The problem is they used a steel that when you go in the cold ocean water like up in the Baltic Sea, you see a ductile to brittle fracture, right? And a ton of these boats actually split in half before they ever left the harbor where they were being worked on. As soon as they put them in the water, a lot of these things actually split right in half because they failed in a brittle fashion as opposed to being ductile. Yeah?
So why are they splitting almost exactly?
You'd have to ask your mechanical engineer colleagues. I am at a loss to explain some of the other details. Some people think this is why, well, some people thought this is why the Titanic, yeah. The Titanic sunk. They said, oh, is it way up north where it's brittle? It hit an iceberg, and instead of just denting, it actually just fractured, and that's why it went wrong. There's now been studies, have been really clever material science studies that actually looked at the rivets, and it was actually really poor quality rivets that they used that actually sheared, and then plates actually probably just fell off. So it probably wasn't ductile brittle transition fail there, but it definitely was with the Liberty ships in World War II. So this is a big deal. Yeah, World War II. So let's talk about our next concept, which is fatigue, right? Fitting for a Wednesday afternoon. Fatigue. Fatigue with materials when they get tired, right? You're using them. Maybe you're doing a cyclic stress over and over. And after a while, it's just like, I can't do it anymore. I've had enough of this stress nonsense. I'm just going to fracture, right? That's basically what's happening. You have some sort of loading condition. It can be a really carefully controlled and repeatable loading condition, like right here, where the average stress is 0 and it, in a very predictable way, goes up and then down and up and down, right? In a sort of sinusoidal function. Or it could be an offset sinusoidal where it's always under tension, but that just goes between high and low tension, right? This, again, is going between compression and tension, right? Or it could just be random, which is the more common scenario, right? Say like temperature, right? Every day, we know that it gets warm in the day and it gets cold at night, but the actual amounts vary quite a bit, whether the pressure system around or whether it's storming, right? So it might look something like this if you look at the thermal stresses that temperature fluctuation causes. So most materials are experiencing cyclic stress conditions, whether you're designing them to or not. Just the fact that we live on a planet where temperature changes means everything's going to have some sort of cyclic stress. Doesn't mean that it's big, but it means there's something. So we need to take into account what this does to a material. Basically, you can calculate the median stress, so your average stress is easily, it's just your max plus your min divided by 2, right? So your median stress is not 0 in this case, but it would be 0 in this case, right? Here's your median stress there. You can also calculate the stress range, which is the distance between your maximum and your minimum, right? So that's your range. And half of the range is what we call the amplitude, sigma A. The sigma A, the stress amplitude, is the one that we usually use when predicting fatigue from SN curves. Let me show you what that looks like. Yeah, question?
Yesterday, at Christian's review, he said that sometimes you just, if there's like a positive part of the stress and a negative part, you just go to 0 for the negative part.
Great.
How do you know when to do that?
We will talk about that in just a moment. Yeah, great question. Basically, when can you ignore the compressive part? Yeah, we'll come back to that. So first off, if you guys are all engineers, you're gonna work for companies, and maybe your boss says, hey, we need to test the life cycle of this thing, right? So put it through 1,000,000 cycles of, compression and tension. What are you gonna do? What does that actually look like as a test? How would you do that? And one way to do it is the cheesy way. Like if you walk through IKEA, you've seen like the robot like closing doors, right, over and over, like opening and shutting like things. That's one way, right? How else could you do it? That's gonna take a long time. Yeah.
Did a couple hundred times on that, the values,
That's a great way. Later this chapter, we do something actually a lot like that. It's called the Larson-Miller parameter. We'll probably get to it on Friday, not today. One way to do it is they take a rod, right? And they rotate this thing, right? But it's not at a perfect 0 angle. It's actually at a slight angle like that. So your rod is actually doing this thing. I mean, this is like very, very exaggerated, right? It's only maybe like a half a degree, whereas this is 10 or something. So if it's at a slight angle and you rotate it, imagine what's happening. On the top, that point is currently under compression as I rotate it, right? Because it's sort of bent in like a V. But when that rotates to the bottom, now it's actually under tension, right? Tension and compression. And then you can just rotate that thing over and over and over and over and over. And eventually it's going to cause a flaw to form at the surface, which will propagate through. So this is one way to do these life cycle tests. I think it's one of the more common ways. There's other ways, but this is one of the common ways. So you do that until it fails, and you keep track of how many rotations it did until it fails. And you generate a curve that looks like this. On the y-axis, you're plotting your stress amplitude, right? And on the x-axis, the number of cycles until it failed. And you can then overlay all sorts of different materials, right? So you've got steel, which exhibits what we call a fatigue limit, and aluminum, which doesn't really. So what is a fatigue limit? If you take a paper clip, which is aluminum, yeah, question or comment?
Is that like a torsion or a tensile
test? It's a type of bending test. It's a bending test that's alternating. It's like an alternating bending test, right? Because if you took this thing, and if I were to start bending it, the top is under tension, the bottom is under compression. And if I switched it, this is basically automating that process by spinning it, right? So you see two very different behaviors. The steel, it reaches what's called this fatigue limit, but aluminum doesn't. If I had an aluminum paper clip, which I always forget to bring with me this day, if I start to bend it back and forth, by the time I do maybe 15 of those, it will snap in half. If I had steel, it wouldn't. First off, it's way harder to bend, but it won't actually snap, right? As long as I stay below a certain threshold. Meaning steel, if I stay below, this looks like 300 meganewtons per meter, I think that's a megapascal. If I stay below 300 megapascal with a steel paper clip, it will never break. But in aluminum, if I just keep on stretching that or flexing it, eventually I'm going to cross below wherever my threshold. Maybe I was like flexing it right here. I'll cross below it, and at that point, I'll have done 1,000,000 cycles, and it will fail, right? So this is pretty interesting. As an engineer, we care about this because you can choose what materials you work with. And if you know that this thing has to survive a gazillion cycles, you don't want to pick something like aluminum because it's going to get weaker and weaker and weaker, and it's eventually definitely going to fail. You'd like to pick something like a steel that has a fatigue limit. What causes a material to have a fatigue limit, we can't answer just yet. In a few chapters, we'll be able to come back to it and talk about some reasons why some materials have a fatigue limit and some don't. So we'll come back to that. Any questions about SN cycles and these plots? So if I said, I need a material, I need aluminum to last 10 million cycles, you would say 10 million is right there, right? Therefore, I better not load it to more than 175 megapascals, right, at the most. Now, what's the problem with this? Do all materials, when you order a batch of 20 bars of aluminum and you were to bend them or stretch them until they break, will they all break at the same stress? Definitely not. There's always variation, right? There's it might be really close variation where there's only like plus or minus a few megapascals, or it might be plus or minus 50 megapascals, right? So how do we deal with that? What do you think? Zach, you got a comment?
I have more of a question. So does it have to do with the cross-section of your sample? Let's say you have a certain amount of grains in your crystal structure, and larger the cross-section, you can have more grains, but it will take longer to fatigue.
Well, stress is the force over your area, right? So let's say you've got like a cylinder and you're pulling on it from the top and bottom, so you're applying a load, F. So your cross-sectional area, if you make it wider, you go to a smaller stress. And so you could design your component. If you know that this thing will break, if you go above 175 megapascals, you could just make your component dimensions larger such that the stress on it is under this value. And typically we do that, and then because we're engineers, we say like, oh, and put a safety factor of 2 or 3 on it. And you say, we're actually going to make it so thick that it should never experience more than 50 megapascals, right? In a few chapters, we'll talk about Weibull statistics, which is a way better way to go about that. Okay, Rosa?
Is that track of other stress amplitude graphs, are those based on the theoretical stress?
No, they're based on actual tests where they actually took a rod, they bent it slightly, something like a half a degree or something. They spun it until they observed some sort of failure, whether that's it deformed over a certain amount or actually fractured. Depends on whether it's ductile or brittle. But no, these are experimentally calibrated. And then to answer the question, maybe how about this? Turn to a neighbor and tell them, how do you deal with the issue of the fact that samples don't all break at the exact same yield stress? They break over a range. What do you need to do to your S versus N curve to account for that? Okay, anybody have a thought? What on earth do we do? How do we account for variability in data with these again, this is called an SN curve, stress versus number of cycles. Anybody have a thought? Or did anybody's neighbor have a great thought and want to sell them out? Nobody? Yeah. Kyle had a great thought. Let's hear. What would you do though? You've got this curve. This is, what do you think this is, first off? Yeah, maybe that's the first question. What do you think this represents? We know, probably, okay, best fit, or in other words, like an average. So like, this might be where 50% failure occurs, right? 50% of your samples is right there. So now how would you account for, if you need to know where not even one could fail, what do you need to do? Anybody have a thought? Yeah, Matt. Lots and lots of testing. You're exactly right. You would have to introduce other lines. You'd have to have another line right here. Would this be correspond to a higher or a lower survival rate as opposed to this one? This one is a higher survival rate. This might be like 1% of samples fail, right? Because say after a number of cycles, right? Let's start the other way. If you're going up from a certain number of cycles to failure, some of them will break at a really low value, but not very many, right? Some of those will break down here at stress low. and some more will break at a higher stress. So you actually, what you really need is a bunch of curves that represent different failure rates, right? 1%, 25%, 50%. So if you find a good provider of, steel or aluminum or whatever, they're going to provide a curve that has various different failure rates, not just one. Because one is just an average, and you don't know what the distribution is from that plot. So you're left to sort of wing it. This is a much more quantitative, better way to talk about failure and SN curves. Can I answer any questions about this? We can move on. Yeah, question?
When you get that piece of still and so you want to do something with it, but you need to know what its fatigue strength is, how do you know which probability you're going to be in, or you just go for it?
Well, let's say that you got this plot, and this is what they gave you, and you know from what your boss told you that you cannot have more than 1%, 1 in 100 fail. What would you do? You know that has to survive this number of many cycles, right? NF, whatever that is, number of cycles to failure. Maybe that's 1,000,000, maybe it's 100, right? You know that you can't design above that stress. You'd stay under it, yeah. Even though you know that's only when one's going to fail, most of them won't. It depends on what your specifications are, right? When you sell a product, if you sell an iPhone, if 1 in 100 are defective, you're not going to do very well, right? If you're selling chalk and you open up the box of chalk and 1 in 100 are broken, you're lucky, right? So it just depends on the application, right? Yeah. Hand over here.
Yeah.
Anthony?
So basically this graph is showing just when these materials will fail on average.
At different rates.
At different rates.
Exactly. So this is all for aluminum, or whatever your material is, steel, whatever it is, right? But at different failure rates, okay? Okay, let's keep going. Some materials, like polymers, can have a really strong dependence on frequency, right? So you're rotating this thing, right? Again, I've got demo, right? I've got this pencil, and I'm going to bend it a little bit, and then I'm going to rotate it, right? So I'm constantly I'm alternating that stress. Some materials, if you rotate this really fast, you'll get a different S curve than if you rotate it at a slower speed. Why do you think that might be the case? Turn to your neighbor and discuss. Okay, what do people think? Why is it that polymers, it depends on the speed at which you spin it, whereas metals less so? Any thoughts? Anybody want to brave a guess? Is it John? Yeah.
Probably wrong, but it's does that have something to do with heat?
It absolutely does. You're definitely not wrong. It has to do with heat. When you stress something, right, you're actually causing atoms to shift around and move, right? You're generating through internal stresses quite a bit of heat. If you were to touch that thing after it's been spinning for a while, if it's been spinning fast, it's going to feel much warmer than if it's been spinning cold. Now, for metals and ceramics that melt at bonkers temperatures, it doesn't matter. For a plastic that might melt at 100 degrees, that could be a significant change, and it's going to change your elastic constant. So, yeah, that's really why. So it's the heat generated can become a non-trivial compared to melting point.
So I have a question.
Okay.
Because when you sing into a glass, sometimes if you hit the right frequency, it can shatter.
Okay.
It also have to do, when you spin it, it also causes micro vibrations. So
absolutely.
To do with, just whatever the harmonic resonance.
Absolutely. I've never even thought about that, but that's absolutely right. Yeah, the resonant frequency, you could be rotating at it, something similar to that, which could cause additional stress multipliers. Okay? All right, so fatigue, when you break something due to fatigue, again, you're cycling it over and over and over. You have to have two steps. You have to start the crack, and you have to grow the crack. So the total number of cycles is going to be Ni plus Np, right? Initiation plus propagation. Stage 1, cracks initially propagate slowly on something called a slip system, which we will come back to. We haven't talked about what that is yet. And then they grow. And they don't grow at a constant rate. They tend to grow in an exponential fashion. I'll show you what that means. Physically, what's going on is, let's say this is your crack initially. You pull under tension, and you actually stretch that crack a little bit. And then when you compress it, you leave behind, you're like one step further than when you started. So it's essentially only growing under tension is what that is. Under compression, it's just closing the crack. it's not usually growing it very much. It's usually only growing under tension. So Rose's question earlier was a really good one. She said, okay, if you're cycling it between, say, positive 100 megapascals and negative 20, what's the range in stress? It's actually only between 100 and 0, because the negative part doesn't actually grow the crack. Anytime the stress is positive, we call that a tension stress, it's going to grow over that entire range. But when it's negative, in this class, we're going to assume that it's not growing. That's an assumption. That's not valid for all materials. It's a pretty good assumption, though. Yeah.
So is that for every material or just for polymers?
That's all materials. For all materials, we're going to assume in this class that they only grow under tension, right? Again, not always the case. Pretty good for this class. It's a pretty good approximation. Okay, because of that, when you look at things that break after fatigue, you see these, they call them clamshell patterns, striations, benchmarks. It's all talking about the same thing. You're seeing a bunch of little lines, and those represent an individual cycle, right? Maybe this was the axle of a car, and eventually it broke. You're seeing individual rotations, right? If it's maybe day to night sequences, you're seeing everywhere where the crack incrementally moves forward a little bit. And if you look at it, the cracks are closer together and then they get further apart. They tend to not be constant. The crack tends to grow faster at the end. In fact, you get something like this. So here's a plot of crack length versus number of cycles for 3 different stresses, right? Which one corresponds to which? Which one's your highest stress? Farthest to the right? Well, think about that. For 500,000 samples, you grew your crack to here, but in this case, after 500 samples, you would have grown to like infinite. It's not even on the plot, right? So actually, this must be your stress high, and then it's getting lower, right? So the stress that you apply will change the crack growth, but generally, regardless of what stress you choose, you're seeing what we call exponential behavior. It looks like a power law, right? It's taking off, right? So even though the crack after the first 100,000 cycles for all of these scenarios hasn't grown that much, the next 100,000 it really can take off depending on what your stress is, right? It's exponential. So we can model that with this awesome equation, which they took out of the 3rd edition because I think you're afraid of calculus. But we're not. We're not afraid of calculus. We can do this, right? This is a differential equation, right? You've got dAdn. So that's the crack. That's the change in the crack length with respect to the number of cycles, dAdn, right? After one cycle, how much further along is your crack? That's what that's basically predicting. Is going to be equal to A. Sometimes they use C. I apologize. As if this field wasn't hard enough, they go and use multiple symbols, right? A or C. Then it's delta K. That's the range in your stress intensity raised to the exponent n. A and n are materials constants. We call those the crack growth constants. So for every material, you could look those up, and people know them, right? And then delta K is just your Kmax minus your Kmin, and K is just equal to Y times the stress times the square root pi a thing. So all we're doing is we're taking the range in your stress. And in this class, we're only considering positive stresses. So if the stress range is between positive 500 and negative 250, your stress range is just 500. If it ranges from positive 300 and positive 100, well, then your delta stress is just 200, right? But we only care about the positive stress because that's when it's under tension, okay? So then how do we do this? Typical failure due to crack propagation plots look like this. You've got this initial region, region 1. That's where your crack starts to grow. Eventually, if you plot this on a log plot, right, this is a log scale over here, and this is a log scale here, then you get this linear region. The reason it's linear is because your equation looked like this. dA dN equals A to the delta K to the N. Question, Rob?
Yeah, so sorry, the next formula, what was the exponent N?
What was what now?
The exponent N.
Exponential N and capital A, those are both constants that you just need to know in order to know how the rate of a crack growing in your material, right? So those are things that I would either give you or ask you to solve for by giving you a plot like this. Now, why does it look linear? Why does this equation look linear when you plot it on a log axis? Well, let's take the natural log of both sides. We now have natural log of dA dN equals the natural log of A plus the natural log of delta K. And then this is, sorry, let me make a little space. N times that. A property of natural logs is if you take two natural logs that are being multiplied by each other, you can add those, right? That's why we put an add there. Yeah, Takar?
Would that be N times LN?
That is N times L and K. That's what it's supposed to be. Let me rewrite that clearer. We brought the n down from an exponent because that's what you can do with natural logs. N becomes multiplied by natural log of delta k. Okay? Or in other words, if you plot the natural log of this, which is our y, and you plot it against the natural log of your stress intensity range, right there, then that should be your slope. Right? This should be x, and this whole thing should be your y-intercept. Right? So it just becomes y equals mx plus b. It becomes linear. If this is not familiar, we will do this many times this semester, so you need to chat with the TAs. TAs, can you raise your hands again? You got Logan, Emily, Christian. If this is not at all familiar, the TAs will make sure this week to go over how to read log plots and make them look linear. Because this will come back over and over with diffusion, with creep, with lots and lots of things that we talk about this class. So you need to learn how to do it. And it's not that bad. Just go meet with them, they'll refresh you. Okay, so now that you got it linear, what you can do, let's rearrange our equation, right? This was our same equation as before. We had dA dN equals A times the range in our stress intensity raised to the n. If you bring the n over and you bring all of this over here, this is called separating your variables. What it's going to allow us to do is it's going to allow us to take the integral of both sides, right? We can take the integral of the left-hand side, and we can take the integral of the right-hand side. The left-hand side has an integral of n, dn, right? The right-hand side, the integral is dA. So we can take two different integrals. On the left-hand side, we're going to integrate from the initial crack size, no cycles, right? Excuse me, from the initial, when you start your testing, to the number of cycles to when it fails. And that's really easy. This integral is easy to solve. It just equals nf. So the number of cycles until it fails is going to be equal to this integral over here, starting from your initial crack size, A naught, remember, that's your half crack length too. That's not your full crack, it's your half crack length. And it's going to increase until it reaches the critical flaw size. Right? When it goes from whatever it started at to the critical flaw size, it will break, right? And so you can figure out, this is pretty great, because we know how to calculate when things will break. Remember? Because we said K1C, a fundamental materials property, equals your y times your applied stress multiplied by pi a. We can solve for the critical crack length, right? By just plugging in, let's say you know what your stress is, your maximum stress. So if it's cycling between 500 and 200, it's going to break when it's at the top of its cycle at 500, right? And then all you have to do is solve for AC. So you know how big the biggest flaw can be before this thing fails. This making sense how this is all coming together? So now you just have to do this integral. It's not that horrible because most of the things can come out of the integral. Only things need to stay in the integral that have a dependence on A. So y technically is y as a function of A over W, right? Remember that from before, that y we can use 1.12, but realistically if A gets big, it would actually have to stay in the integral. So if I tell you that you can assume y stays the same, go ahead and take it out. It'll make your life easier. If on like the homework you have to leave it in on one of the questions, then you have to leave y in and you're going to have to do a much harder integral. Don't do that by hand. Plug it into Wolfram Alpha or MATLAB or the software you're choosing. Right? Just do it by hand and then print it off and put it on your homework. Okay? Can I explain anything up till now? Yeah.
Natural law and linear law, is that going to be finding delta K or A?
Great question. What do we use the whole make that power equation look linear for? What you do that for is to figure out what big A and little n are, right? Because you could figure out the slope of this line in this region 2, which is where the crack growth equation works. Since you know the slope of that line, you can figure out n, right? N is the slope. Once you know that, you can figure out capital A. So the whole reason of plotting it this way is it allows you to figure out what your crack growth constants are if I don't tell you them. I might just give you this figure. In fact, I think I do on the homework, on one of the first homework questions. I've just given you a bunch of data. You need to, from that data, figure out what capital A and little n are, your crack growth constants. Once you know those, you plug in capital A and little n and all these different values to calculate the number of cycles to failure. Are there any other questions I can answer about this? We will do an example in just a moment. Yeah?
Just real quick, could you go over the significance of the scaling on that chart again?
The scaling, can you tell me what you mean? Oh, why? So this is plotted on a log scale, right? These are not a linear scale, it's a log scale. because of that, it allows us to plot this whole term as just y. And because this is on a log scale, we can take this whole natural log of delta k and just call it x. So it makes something that has an exponential and it makes it look linear. Yeah, Arthur.
Capital A pound and 3 pounds on the root of that function.
So there's lots of ways to solve for it. I think the easiest is to figure out the slope. Some people will just take 2 points, right? They'll take that point and they'll take that point, and they say, I've got 2 equations, I've got 2 unknowns, I can just like bust this thing out. If you want to do that, that's great. That works as well. Okay? Let's do an example. Here's a table of common crack growth constants for a bunch of materials, right? So different materials, different metals. Here's how these basically are telling you how your crack is going to grow in both metric and imperial, right? We're going to use metric. We're not barbarians. Okay, the question is this. We've only got 6 minutes. We'll see how far we can get. A steel plate has a fracture toughness of 80 megapascal root meters. It is alternately loaded between 500 megapascals in tension and then 60 megapascals in compression. So it goes positive 50 to negative 60. If A and N are given, what is the largest tolerable flaw size that if the cone, so yeah, what is the largest tolerable initial flaw size, I should say? That it can be if your part has to survive 10 years being cycled once every 5 minutes, right? Where do you even begin on a question like this? Let's just work it together. Well, first off, let's figure out how many cycles it has to survive. 10 years, right? It has to survive 10 years, being once every 5 minutes. So how many minutes are in 10 years? Well, in 1 year, there are 365 days. In 1 day, there are 24 hours. In 1 hour, there are 60 minutes. And then we're going to do every 5 minutes, we have a cycle. Okay? Everything cancels out, and you're left with just number of cycles. So when I do this, I get 1.605 times 10 to the 6th cycles. Right? So it basically, you're asking it to survive 1 million cycles. Okay? Okay, in order for it to survive 1 million cycles, we've got that part of the question down. What else is it asking? It says, what is the largest tolerable initial surface flaw that you can have? Since you know the crack growth constants. Basically, that crack is going to grow, and after 1 million cycles, it better be exactly at the critical flaw size, right? Or smaller. Make sense? So I'm asking you to solve for A naught in this question. So let's go ahead and start plugging in things we know. NF is 1.065 times 10 to the 6th cycles. That's going to be equal to 1 over A. I don't remember. Let me pull it up. I did this before class. Oh, sorry, it's 1.05. 1.05. It is to the positive 6th power, though. Sorry, 1.05. Okay, so it's 1 million cycles, okay? We plug in A, right? A is equal to, in this case, 1.62 times 10 to the negative 12th meters per cycle. So let's do 1.62 times 10 to the negative 12th. That's going to be multiplied by pi to the n over 2. N is 3.2. Divide that by 2 and it's 1.6. The change in stress, what are we going to use for our delta sigma? What will we use for our delta sigma? What's the range in stress? It's going from positive 500 down to negative 60, but the crack only grows during the positive portion. Yeah, question, Spencer?
I just considered it from 0 to 500.
Yeah, 0 to 500. So our range is just 500 megapascals. So 500 megapascals. That's raised to the 3.2, right? We're going to take our integral from our initial flaw size up to our critical flaw size, dA, divided by y to the 3.2, multiplied by a to the 1.6. That's 3.2 divided by 2. So we could solve this, except we need something else. What do we need to know still? Well, you have one equation so far, and we have 2 unknowns. We have A naught, which we really want to solve for, and we have AC. How do we figure out what AC is? Yeah, Rosa, question? Exactly. You're going to use the fracture toughness equation. You're exactly right. You're going to say that K1C equals y times sigma multiplied by the square root of AC. We can solve for the critical flaw size by plugging in our maximum stress, which is going to, when it fails, it's going to fail at 500 megapascals, right? It's going between negative and up to 500. It's going to fail at the top of that cycle. We can plug in 1.12. We can plug in the fracture toughness, which I think was 80. Yeah, 80 megapascal meters. So you can solve for the critical flaw size in meters. Okay, when you do that, I end up with my critical flaw size equals, I get 0.00649 meters. And we will finish this next time because we're out of time. So this will be the first clicker question of the next class.